Good morning all. This is Satish Kumar, Assistant Professor of EC Department. Now let us see the video lecture series on Introduction to Discrete Fourier Transform. See empathy part. First, defects in signals is to be identified. Conversion from time domain to frequency domain to takes a longer time. Frequency domain information must be extracted. Next one, D is discrete Fourier transform process. First, Fourier series. From the Fourier series, we can going to analyze the Fourier transform, and then discrete Fourier series, and then discrete time Fourier transform. With the help of discrete time Fourier transform, we can going to analyze the DFT, and then FFT, fast Fourier transform. This is the discrete Fourier transform process. Next one, Fourier coefficients representation. First represents the Fourier transform of function s of t. First, time conversion of time domain into frequency domain. When we apply the Fourier transform of time domain, which can be converted into frequency domain. Second one, transformation of the periodic summation of x of t, Fourier series coefficients. And then transformation of periodically sampled s of t, discrete time Fourier transform, and finally we can going to taking the Fourier transform of both periodic sampling and periodic summation, we can get the discrete Fourier transform. From the discrete Fourier transform, we can going to analyze the fast Fourier transform. Next one, discrete Fourier transform. For a discrete time sequence, we define two classes of Fourier transforms: discrete time Fourier transform, discrete Fourier transform. The DTFT for sequences having infinite duration, the DFT for sequences having finite duration. Next one, DFT can be defined as x of omega is equal to DTFT of x of n. Summation n is equal to minus infinite to plus infinite x of n into e power minus j omega n. Infinite inverse DTFT is nothing but I DTFT is equal to x of omega is equal to 1 by 2 pi integral over minus pi to pi x of omega into e power j omega n into d omega. Now we can going to see the discrete Fourier transform. Discrete Fourier transform, we can going to convert the time domain into frequency domain. Next one, representation of signals. This is the time domain representation with respect to time and amplitude in terms of 1 kHz. The once full cycle can be represented by t. In terms of frequency domain representation, 1 kHz. It can be compressed into 2 kHz. The one waveform can be compressed into two waveforms, that which is equal to t by 2, t by 2. The amplitude of frequency domain representation will get 2 kHz with respect to amplitude and frequency. Next one, discrete Fourier transform. The DTFT x of omega is periodic with period 2 pi. The frequency omega is the digital frequency, therefore it is limited to the interval minus pi less than omega to less than plus pi. The digital frequency omega is the normalized frequency relative to the sampling frequency defined as omega is equal to 2 pi into f divided by fs, which is equal to minus fs by 2 to plus fs by 2 with respect to minus pi to plus pi. This is the one period of x of omega. Next one, DFT representation from the time domain with respect to x of n to m, that can be converted in terms of frequency domain to minus 3 pi to omega, which is equal to x of e power j omega. Next one, discrete Fourier transform. In discrete Fourier transform, given sequences as x is equal to 0, 1 up to n minus 1. In terms of it is a finite sequence, therefore capital X is equal to DFT of x of 0, x of 1 up to x of n minus 1. Therefore, which is equal to x of k is equal to summation n is equal to 0 to n minus 1, x of n into wn into k power, and wn represents e power minus j 2 pi by n. Therefore, summation n is equal to 0 to n minus 1, x of n into e power minus j 2 pi kn divided by capital N. When we giving small x to the DFT sequence, which can produce the output as capital X. Small x represents time domain, capital X represents frequency domain. The inverse DFT, same. Fourier transform giving the sequence capital X is equal to 0 to n minus 1. Therefore, X is equal to IDFT of capital X, small x to x of 0 to x of n minus 1. When we giving the capital X to the x of k to the IDFT, which can produce the output as x of n. Capital X represents frequency domain converted into time domain. X of n is equal to 1 by n. Summation k is equal to 0 to n minus 1 x of k into e power j 2 pi k n divided by capital N. The discrete Fourier transform pair. The DFT and IFT forms the Fourier transform pair when with small x given to the DFT, which can produce the output as capital X, x of n, x of k. Same x of k can be applied to your inverse discrete Fourier transform, which can produce as x of n. Small x represents a time domain representation, capital X represents frequency domain representation. The DFT is a numerical algorithm and it can be computed by the digital computer. Next one, this is the representation of DTFT and DFT. First, x of n with respect to n. This represents small discrete time signal. While we applying the DTFT of x of n, which can produce the output as 0 to 2 pi with respect to omega. For the above discrete signal, we can going to find the discrete Fourier transform. That is, it can be represented by discrete time with respect to 0 to n minus 1. 2 pi divided by n with respect to k. Next one, properties. These are different types of properties of DFT. Linearity, time domain can be converted into frequency domain. A into x1 of n plus b into x2 of n. That can be converted into a into x1 of k plus b into x2 of k. In frequency shifting, x of n minus 1 converted into e power j 2 pi km into x of k. Frequency shifting, e power minus j 2 pi k naught divided by n into x of n, x of k minus k naught. Time reversal, x of minus n, that can be converted into capital X of minus k. Conjugation, x conjugation of n is equal to capital X conjugation of minus k. Time convolution, x of n into x2 of n, which can produce x1 of k into x2 of n. Frequency convolution, n term that can be multiplied with 1 by n into x1 of k into x2 of k. Next one, these are the applications of DFT, spectral analysis, image processing, signal processing. Other applications such as sound filtering, data compression, partial differential equations, multiplication of large integers, etc. Next one, define DFT. DFT is nothing but discrete Fourier transform. It can be represented as x of k is equal to summation n is equal to 0 to n minus 1 x of n into e power minus j 2 pi k n divided by capital N. What is mean by inverse DFT? If we inverse discrete Fourier transform, which can be represented x of n is equal to summation k is equal to 0, 1 by n into summation k is equal to 0 to n minus 1 x of n into e power plus j 2 pi k n divided by capital N. Give some applications of discrete Fourier transform. It is used in spectral analysis, image processing, signal processing, and then data compression, partial differential equations, etc. Define DFT pair when we applying the x of n to DFT, which can produce this as output as capital X of k. That capital X of k can be applied to inverse discrete Fourier transform, which can produce the output as time domain representations x of n. The DFT, discrete time Fourier transform for sequences having infinite duration. Mention the properties of DFT. Properties: linearity property, time shifting property, time scaling property, frequency shifting property, conjugation property, convolution property. Thank you.